look at me like I'm crazy when I shut my feelings down. You look at me like I'm different. Still you stay cause you feel something real. Get so lost in my moments. Doesn't mean I don't need you. I fell in love with your colors. They kinda tell me what I'm thinking. Fell in love with the way we are and the way we lose it. There's something different about us, and the reason why we stay. We fly around like paper planes. We never know where we will fall. Nobody can see us, still they wanna tear us apart. There's something different about the way we are. There's something different about us. 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 We're pouring cup after cup after cup. Yeah, it's just the way we do it. Anything just to block out the real life, real life. Yeah, we're loving the way they think we're so messed up. Even if what we're doing is bad, there's so many emotions. Sharing stories that we never had, yeah, none is real. I think we're searching for reasons not to be like them. We fly around like paper planes. We never know where we will go.
Hey, good morning.
Nobody can see us, still they wanna tear us apart. There's something different about the way we are.
How are you all doing? It's Monday. We survived the storm.
About us. There's something different about us.
How much rain did you get? Let me look at my engage. We got. It'll reset because it resets every 24 hours. But I think last time I looked, last night, we had almost 4 inches, and now we've added another 0.39, so about 4.5. Whoa. Well, I should probably let you know, I'm trying something new today. Not only am I doing the usual Zoom thing, I'm also simultaneously streaming this to YouTube. So we've got some people who are watching who are not in our class, but are all scattered all over the world. Like I did this last Thursday as an experiment, and we had people from India, Pakistan, Switzerland, Germany, of course the United States, Brazil, and those are the ones I just remember. So at least 5 countries right off the bat. So I guess what I should let you know is, since there are people who are not in the class, try to refrain from talking about anything that's like specific to like where you live or like, you know, where your kids go to school or anything like that. They can hear you, but they can't see you. So I don't have like your Zoom windows put up on the YouTube stream. It's just me. So they can hear you, but they can't see you. And also, I was going to say, if anything does come up that's like private, I can just mute the YouTube stream so that they can't hear or see anything. So if that ever comes up, I'll just hit a button and then it gets blanked out on the YouTube side. Are we good with that? And the purpose of this is in part because, you're here. Yeah, you said that you had problems listening to the stream. Excuse me, had to sneeze there. You had problems downloading the stream after the class because the file was just so huge. And so by putting it up on YouTube, it can then give you whatever quality you need to be able to watch the video. So it can, slow down the video or give you a reduced quality in order to get it to fit within the bandwidth that you need. So we're all good with that? I don't hear anything. Yeah? So currently we have 3 people watching. Yes, on Thursday we had up to 17. That was pretty cool. Oh, that's on Zoom, right? On YouTube, there's 3. Now they're down to 2, so we'll see how it goes. I'm going to make the music really quiet. Okay, so we're on to a section called Discrete Probability. And this is kind of like the flip side of the combinations and permutations. What we were doing last week was calculating how many of something there was, like how many passwords or how many people fit this criteria. What we didn't do was calculate probabilities, like what's the chances. In fact, it seemed like the pigeonhole principle was almost like probability, like how long does it take before something repeats. And there's a great tendency to maybe calculate that as a probability, like, oh, I've seen a lot of students answer the question as a probability. Like, it's pretty likely that 2 people will have the same password, but that's not what we're asking. We're asking how long do you have to go before there's a guarantee, or how many passwords do you need to generate before there's a guarantee to have a repeat. Now we're actually talking about probabilities. What's the probability that something is going to happen? So let's start with some warm-up questions. So I want the people who are interacting with me to just post the answers. You can put it in chat or you can say it, and we'll see where it goes. All right, so here's a set of warm-up questions. You are driving a car and you're going through these intersections, and there are traffic lights at each one of these intersections. And you know what it's like to drive those intersections, right? Either you go through all the green lights, or it seems like you hit every single red light. But for now, let's just assume that all the traffic lights are independent of each other. So the color of one light that has no impact at all on the color of any of the other lights. And there's also an equal likelihood of a red versus a green light. We're not talking about yellow lights right now, so don't worry about yellow lights. Just the lights are either red or green. So there is a 50% chance of it being green and a 50% chance of it being red as you encounter each intersection. What's the probability of all the lights being green? So you hit a green, a green, a green, a green, and a green as you go down the street. What's the probability of all the lights being green? Uh, 1/32 is correct. So here's how you figure that out. I'm going to use P to stand for probability. Now I know your textbook uses PR, but that's just like way too much writing. Also, P is used to mean permutations, so just realize that in this section we're talking about P meaning probability. So it's the probability that all 5 lights are green. In other words, that you get 3 or 5 greens in a row like this. Probability of a green, followed by a green, followed by a green, followed by a green, followed by a green. And we can separate this out into the probability of a green here's where the ands and ors come in really important. The probability of encountering a green on the first light, and the probability of a green on the second light, and green on the third light, and green on the fourth light, and green on the fifth light. So we got 5 lights altogether. What's the probability of getting green and green and green and green and green? Well, this is just the probability of getting a green light raised to the 5th power. And that's 1/2 to the 5th, or 1/32. Right, we're assuming here that only reds and greens exist. There's no other colors for now. Next problem, what's the probability of at least 4 of the lights being green? So you go through all 5 lights, and you want the probability that at least 4 of them are green. It is not 1/16. Anyone else? No. Oh, you're closer, I think. So to do this problem, we're going to have to count all the ways that we could have at least 4 greens in a row, and then figure out the probability of each one of those. So to get 4 greens in a row, there are 3 ways. No, sorry, no, it's more than that. There's 5 ways to get 4 greens in a row. So you've got the first 4 are green, and then there's a red at the end. And another one is what am I looking at here? Oh, you got a green and then a red and then 3 more greens. Maybe you got 2 greens, a red, and 2 greens. All right, so basically you've got 4 greens, and you're just changing where the red is occurring. Okay, so there's 5 of those, and then there's 1 more. That's a probability that all 5 of them are green. Okay, so you got 5 of these where there's 1 red, and then there's 1 more possibility where none of them are red. And that gives you at least 4 greens. Okay, so what's the probability of this first possibility happening? 4 greens and then a red. Well, this is a half, and this is a half, and this is a half, this is a half, and this is a half. So this is 1/32. And then the next one is also 1/32, and the next one is over 1/32. Then there's the 2 missing ones that I didn't write. And then there's the final 1/32. Okay, so why did I use plus here? Well, remember, plus kind of like means or. So we got the probability of a green and a green and a green and a green and a red, or the probability of a green and a red and a green and a green and a green, or the probability of a green and a green and a red and a green and a green, and so forth. So this comes out to 6/32 or 3 over 16. Okay, with that problem-solving technique in mind, let's do the third problem. What's the probability of exactly 3 greens all in a row? So you go through all 5 lights. What's the probability of encountering exactly 3 greens in a row? Yes, 3 over 32. Perfect. How'd you get that? Yeah, I think so. So probability of 3 greens and then 2 reds plus the probability of a red and then 3 greens and then a red plus the probability of 2 reds and then 3 greens. So that's the only 3 ways you can get 3 greens in a row. And then this is over 1 over 32. This one is 1 over 32, and this one is 1 over 32. Okay, so we've got those techniques down. Now let's change things up a little bit. Let's change some of the probabilities. So now let's say that the probability of encountering a red is now 0.6. And therefore, the probability of encountering a green is 0.4, because we're not counting yellows at all. So let's redo problem number 1. What's the probability to get all green? So we're redoing the first problem, but with a different set of probabilities. Let's see, good. Forrest, you got that? Okay, so this is the probability of getting 5 greens, which is now 0.4 to the 5th, to 0.01024. And then let's redo problem number 3. What's the probability of 3 greens in a row? So for this problem, you still set it up the same way. You just have to plug in different numbers. Right, try it again. 0.14, not correct, but you see what you did. So try it again. There we go. That's what we're looking for. Okay, so to solve this first probability, this is the probability of a green, which is 0.4, and then another one, and then another one, and then the two reds. And then we'll just multiply those by 3 because the probability of the other two work out the same. So we get 0.02304 times 3, and that gives us a total of 0.0, what'd you get? 0.0691. Okay, so that's independent probability, where the probability of each one of those events happening doesn't influence the probability of any of the other events happening. But at least the way that the traffic lights are set up in most cities in the United States, the traffic lights are dependent on each other, that the color of one influences the color of the other, another one, and that allows you to drive down the street following all those green lights as you go, or following all the red lights, right? So now we're going to shake it up a little bit with some different probabilities, but set up what's called conditional probability. So we'll start out by saying the probability of the first light being green is 0.4. So, given that, what's the probability that the first light is red? Again, we're not talking about yellows at all. So that would be 0.6, right? These have to add up to 1 because the traffic light is either red or green. It's some color. There's a 100% chance that it's some color. There's a 40% chance that it's green and a 60% chance that it's red. Now, this one here uses the bar, and it means given. The bar means given. So what's the probability, or I'm going to tell you that the probability that the second light is green, given that the first light is green. Okay, so the first light is already green. The probability that the second light is green is 0.75. And if the first light is red, the probability that the second light is red is 0.9. This is what it seems like when you're driving down the street, right? Okay, so if the first light is green, the probability that the second light is green is 0.75. And if the first light is red, the probability that the second light is red is 0.9. And we want to calculate what's the probability of the second light being red given that the first light is green. Okay, so there's two ways we can do this. One is we can see that if the first light is green, well, then the second light, what am I trying to say here? If the first light is green, so these two probabilities match up right here, right? If the first light is green, then if the second light is also green, there's a 0.75 chance of that. So if the second light is red, there must be a 0.25 chance of that. Okay, because that second light is either red or green. If it's not green, it must be red. So if there's a 0.75 chance of it being green, there must be a 0.25 chance of it being red. Okay, and that's one way to calculate this. The other way that I want you to actually pay attention or learn is to draw a tree diagram. So we'll draw it like this. This first circle here represents the first traffic light. We'll call this L1. And that first traffic light can be either red or green. And there is a 0.4 probability of it being green and a 0.6 probability of it being red. So once you go through that first traffic light, there is then the second traffic light. We'll call this L2. And that one can be either green or red. And on the green branch, there's a 0.75 probability of being green. And on the red branch at the bottom, there's a 0.9 probability. I got these numbers from the numbers that I gave you. Okay, so there's 4 ways to go through this tree. You can start at light 1 and go green, green. You can start at light 1 and go green, red. You can start at light 1 and go red, green. Or you can go red, red. There's 4 ways to go through that tree. Each one of these pairs of branches needs to add up to 1 because there's a 100% chance that the first light is either green or red, and there's a 100% chance that the second light is green or red. If we know that there's a 0.75 chance of that second light being green, there must be a 0.25 chance of it being red. And that's where we got this. Okay, how about that second light being green if the first light was red? That's this here. If the first light is red, what's the probability that the second light is green? 0.1, good. And that's because these two numbers here have to add up to 1. Okay, with that tree in mind, now we can calculate some more interesting things, like what's the overall probability that light 2 is green? You figure it out? .36? Yes, that's correct. How did we get that? Well, looking at the tree, there's 2 ways to get to a green light on the second light. We can either go through this branch, or we can go through this branch. So we've got the probability of encountering a green followed by a green, or the probability of encountering a red followed by a green. So there's 2 ways to get to a green light on the second light. Either the first light is green and then the second light is green, or the first light is red and then the second light is green. Okay, the probability of getting green, green is 0.4 times 0.75. And then the probability of getting a red followed by green is 0.6 times 0.1. And that comes to 0.36. So that was about a 1/3 chance of that second light being green overall. Next problem. What's the probability of the second light being red? And there's two ways to calculate this. Anyone? Good. How'd you get that? Yeah. So if the second light isn't green, it must be red. Right? There's a 100% chance that it's either green or red. So we can just subtract 0.36 from 1 and get 0.64. But then you said you double-checked your answer because you can look at the tree diagram and see that there are two ways to get to a red light. You can go green-red or red-red. So green-red is 0.4 times 0.25. And then red-red is 0.6 times 0.9. And you get the same answer. Okay, so now that you've learned about that tree diagram, let's calculate the probability for light 3, that third light out of a sequence of 5. Now let's just for now assume that light 3 behaves similarly to light 2 in that its probability depends upon the previous light. So same probabilities as up here, except that just replace 2 with 3 and 1 with, 2 with 3 and 1 with 2. What's the probability that light 3 is green? So to figure this out, we could draw a tree diagram again, starting with light 1, and then branching off to light 2, and then those branching off to light 3. And then there would be 4 ways of going through that tree, and we'd calculate all those probabilities. But we can actually shortcut this a little bit because we've already figured out the probabilities for light 2. So we can just start there. We know that the probability that light 2 is red is 0.64, and the probability that light 2 is green is 0.36. Right? We got those from our calculated values here. And then we'll put in light 3. which can be either green or red. And then light 3 is going to behave similarly to light 2, so its probabilities are 0.75 up here, 0.1 here, 0.25 down here, and then 0.9 on the bottom. So the probability that light 3 is green, again, there's 2 paths through this tree. And we get 0.36 times 0.75 plus 0.64 times 0.1. So those are these 2 paths through the tree. And if we calculate that all out, we get 0.337. Okay, so you can see, if you compare these numbers, they probably went down a little bit. So, a little intermission here. The people on YouTube are wondering where I've been. See, I used to do live streaming quite frequently. Like every Saturday night or Sunday night, I would just get on the computer and just start like streaming something. It could have been like streaming preparation for the next week, or I could have done a review of the previous week's material, or a little preview of the next week, or sometimes it was just me getting my assignments ready. And in some cases, for programming classes, it means I've got to write the program first. So I'd kind of like play around and just make sure that the program was going to work, and I'd live stream that. And then about 6 years ago, I just stopped, right? I didn't have time to do that anymore. And so I've been kind of off the air for a while. And now that I have started streaming on YouTube again, I have people who are waiting. And I've got like 20,000 subscribers on YouTube. Don't get any money for it, but I got about 20,000 people. And some of them have it set so they get a notification every time I go live. And so on Thursday, I hit the go live button, and then like 5 people or 6 people just immediately jumped in and just said, hey, where have you been all this time? And I said, well, I've been on Zoom. So here I am trying to do live streaming to YouTube again. And what you're seeing, for people who've asked, like, what's going on here, this is a course in discrete structures, and we're talking about discrete probability. So mostly kind of like mathy topics, although there will be some computer programming. If you follow along, there will be some programming later on, but right now we're doing mathy stuff. But this is discrete structures. We're talking about, it's kind of like discrete math, but for computer science. So this is discrete probability. Discrete probability is about calculating statistics and probabilities for events that either happen or don't happen, or have 3 states, like a traffic light is either red, yellow, or green. Or it could be like, it's either raining or it's not raining. Or it is, what would be, probability of a given password being, let's say, ABC or XYZ, right? So you've got discrete events that either happen or don't happen, and we're calculating the probabilities of that. Okay, so it probably goes without saying, I've kind of said this a couple times, that when you sum up all the probabilities of a given set of outcomes, those must add up to 1, representing 100%. So if you've got some variable A that represents an event that either happens or doesn't happen, or has 3 or 4 different states, all those probabilities must add up to 1. So for example, if I have, let's say, an unfair coin and I toss it, the probability of it coming up heads is 0.55. What's the probability that it comes up tails? Again, either heads or tails, right? No other possibilities there. 0.45, good. Well, let's calculate that. So let's say the probability that comes up heads is 0.55. The probability of tails is 0.43. What is the probability that comes up on its side? Yeah. And then weather. Let's say there's a 0.5 probability of it being sunny, 0.3 of cloudy. What's the probability that it's rainy? So to put it more generally, if there is a 0.3 probability that event A happens, what's the probability that event A didn't happen? Yeah, 1 minus 0.3 is 0.7. Okay, so to put this in context, why we're studying this, or what's my vehicle for studying this, I want to talk to you about spam filters. Now, most of you have some experience with spam filters. Those are programs that are carefully guarding your emails. Every single email that comes into your email provider, whether it's Gmail or Yahoo or whatever your ISP, they probably have a spam filter that looks at the contents of your email message and determines if it is spam or not spam. Now, increasingly, we've also got spam filters on messaging applications like, WhatsApp and iMessage. It can send you, when you receive a message, like my phone sometimes says, this appears to be spam. Do you want us to just, hide these? And I go, sure. So your phone is learning what spam looks like. So a little bit about the history of spam. First of all, it started back around 1995 or 1996 was when the very first spam message was sent. And I think at the time the subject was called Make Money Fast. And millions of people were sent this spam message, and there was a huge outcry that the internet finally went from just being this medium for exchanging information to finally, oh my gosh, now the scammers are here. And so what system administrators did at the time was they wrote rudimentary spam filters that would look at the words coming into for a particular email, and they would look for common phrases. Like if we saw the subject go by "make money fast," then we would just flag, and I say we because I was actually a system administrator at this time, so I was participating in this goal of making spam filters that worked better. I was kind of on the receiving end. I was trying to write my own spam filters, but also learning from what other system administrators around the world were doing at the time. So I wrote this program that would scan for certain phrases in the email message, and if it saw that phrase, it would tag the message as spam and drop it into the spam mailbox. And if I didn't see those phrases, I would let the message through to go into the regular inbox. And it didn't take long before spammers started doing things like changing the wording of their messages just a little bit. It could be do something like change the spacing of the words, change the capitalization, convert some of the letters to numbers. These little things that would make it so that the filters didn't work anymore because they were doing exact matches on phrases, and if it didn't exactly match, it would get through. So it wasn't long also before system administrators started developing their own programs and sharing them amongst themselves. At the time, there was a program called Spam Assassin. And the way it worked was it would scan your messages, but you could download a list of common phrases. And every day I would get up, come into the office, go download the latest list, plug that into Spam Assassin, and let that go to work. And where these lists came from was other people, as they were using their spam filters, they would see messages come in, they kind of write down the common phrase that appeared in that spam message and include in that list. So those lists get longer and longer and longer as the months went on and the years went on. It got to the point where the spam filter was spending more time scanning the message, or I should say the rate at which the spam filter could scan messages was slower than the rate at which messages were coming into the system. Okay, so let's say there were 10 messages per second coming into the system, but the spam filter could only filter 5 messages per second. So that meant that there was now this huge backlog of messages. Sometimes it would take hours before your message could be delivered into your mailbox because it was just queued up waiting to be scanned. This became to be a huge problem of like whack-a-mole. Not only is the spam filter getting slower and slower because the criteria list is getting longer, but also the volume of messages is increasing, and it's getting harder and harder to keep up with the spammers because now we got to download these new lists like multiple times per day. In fact, we automated it. We just had a program that would launch every couple of hours and go download the latest list and bring it into the spam filter. So it became a huge problem, and so the problem is maintaining that list of common phrases that are in spams, and there's the problem of the volume of emails getting to be too much for the spam filters to keep up, and then we actually dedicated an entire computer just to scanning emails. It's a very expensive thing to do, but a good benefit for our users. And the spammers were always tweaking their messages a little bit. They would download the same lists and then run their messages through that same filter, and if it got caught, they would change the message a little bit so that it didn't get caught. So it was this cat and mouse game where every time the spammers figured out a new way to get through the filter, the sysadmins would figure out a way to stop it, and the spammers would figure out a new way to get through the filter, and just kept escalating from there. So what spam filters needed was not like a human writing down all these common phrases, but some sort of automated way to detect when messages were spam and not spam. In fact, one that could learn over time rather than having a human intervene and download new filter lists. And that's when spam filters really took a great leap in functionality, because they introduced this idea of a spam filter that could learn over time. So before I get into that, let's look at a couple of sample emails. So here's 3 emails, and if you look at the one on the left, how would you, as a human, classify that? Would you think it's spam or not? What do you think? Looks like spam. So what do you see in that message that kind of gives it away? All right, so it's not really the American way of saying things. What do you see in there that isn't raises your red flags? It's really hard for computers to ascertain formal versus colloquial. But do you see any words in there that you wouldn't use in normal, everyday emailing? Yeah, solicit, virtue, top secret maybe, yeah, confidential, stuff like that. So we could be pretty confident to label this as spam. What about the second one? just because there's a $sign right there? I mean, that could be one thing that you might look for. It wouldn't necessarily be the giveaway, right? But it could be one of many things that you'd be looking for. And if you cross some kind of threshold, then you would say this is spam. And if you're under that threshold, then it's not. What else could be in there? I mean, I see it's written in all caps. That'd be an easy thing to check for. The all caps is priceless. What else? Things like 99 million email addresses, remove into subject. And so we can call this spam. What about this third one? Which one, the second one or the third one? Okay, I know this is blatantly off topic, but I'm beginning to go insane. Had an old Dell image of XPS sitting in the corner. Yeah? So, again, it's hard to teach a computer about grammar and informal versus formal, but I think I didn't see who said that, but they seem to be pretty good. There's not any out. Yeah. So you might see a few things that look unusual, but it doesn't maybe strike you as being that unusual, particularly if this is the way that one particular person happens to write to their friends, right? So we can probably say this is maybe not spam, although, it could be a little dicey, excuse the pun. In system administrator spam filtering jargon, if a message is not spam, it is called ham. That's really truly what it's called, right? So you've got spam, which is the bad stuff, and ham, which is the good stuff. But if you're from Hawaii, you might disagree with me on that. So this form of a spam filter that can learn over time is called a Bayesian spam filter, because it's based upon Bayes' rule, which is a way of calculating conditional probabilities. You can kind of, in some cases, avoid drawing that whole decision tree. So Bayes' rule says that you can calculate the probability of event A happening given that B already happened using this formula right here. And one of the things I notice about the formula is that the order of the events is flipped. So it's kind of like if you look at a problem and you can see that the probabilities have been given in a certain order, and you want to calculate the probability of it in the other order, you can do that with Bayes' rule. Another way of stating this is that what Bayes' rule allows you to do is calculate the probability of the cause, A, given the evidence, B. And where Bayes' rule really kind of took off was in medical diagnostics. See, it wasn't that long ago, 20, 30, 40 years ago, when if you went to a hospital and you felt a little ill, the doctor would kind of use his or her intuition and come up with a diagnosis. And from that diagnosis would then make a course of treatment. But it was all based upon a hunch, right? Until people started collecting hard data about people coming into the hospital, what their symptoms were, whether or not the treatments worked, which treatments they were prescribed, and they started collecting all these statistics. And they realized that if doctors could be trained on how to do diagnosis using hard facts, then they can make better diagnoses. So someone might come into the hospital with some disease of some sort, and we can say that this disease is not observable. right? The disease is inside the body somewhere. We can't just see it, but we can run tests and we can look for symptoms. So we can say that, using this arrow, that the disease causes the outcome of the test, right? The outcome of the test will either be positive or negative, depending upon whether you have the disease or not. The test is observable. We can see the results of the test. So we can say that this is the evidence. That's what I mean up here. So we can calculate the probability of the cause of having some disease given whether or not the test, the evidence, came out positive or negative. So to translate this picture into Bayes' rule, we would say the probability of having the disease given the outcome of the test is equal to the probability of the test given the disease. So you just flip those variables around, times the probability of the disease over the probability of the test. Okay, so I'm just taking these letters, D and T, and plugging them into Bayes' rule up here. Okay, so let's put this Bayes' rule into action. So let's say you're trying to come up with, or you have a test for to detect whether or not someone has a specific kind of cancer. Now, I just kind of made up these numbers. They're numbers that work out pretty well. They're, not based upon any specific cancer, but, they're probably reasonable. So I'll use C to indicate whether or not someone has cancer. I'll use plus to indicate that a test came out positive, and minus to indicate that the test came out negative. Now we know overall, based upon statistics that we've collected over years, that the probability that any one person in the population has this cancer is 0.01, a 1% chance. And we know that the probability of a positive test, given that you have the cancer, is 0.9. So we can say that the test is 90% accurate. And the probability of a negative test, given that you don't have the cancer, is 0.8. So these are the true positives and true negatives. So let's draw out that tree diagram. First thing is the cancer, and the reason why we know the cancer comes first is from our diagram here. So this thing points to the test, and in the same way, the cancer here is going to point to the test. So you either have cancer or you don't, and the test can come out positive or negative. And we can start labeling each of the branches of the tree. We know that the probability of having cancer is 0.01, and the probability of a positive test given cancer is 0.9, and the probability of a negative test given not cancer is 0.8. So whenever I give you one of these problems, there's almost always going to be 6 numbers in the tree. 1, 2, 3, 4, 5, 6. There's 6 branches in the tree. I'll usually give you 3 of the numbers, and you need to calculate the other 3. Just do that right off the bat. Don't worry about whether you're going to need those numbers or not. Just go ahead and calculate those. So the ones we're missing are these three. And that's the probability of not cancer, the probability of a negative test given cancer, and the probability of a positive test given not cancer. And each one of these rows should add up to 1. Okay, so the probability of not cancer is 0.99, right? These add up to 1. That's also adding up to 1 here. The probability of a negative test given cancer is 0.1. And the probability of a positive test given not cancer is 0.2. So now we've filled out this tree entirely. Okay, so patient comes into the hospital, says, I don't feel so good. Doctor says, you might have cancer. Let's run a test. So I'm going to calculate what's the probability you actually have this cancer given that the test came out positive. So they run the test, comes out positive. What's the probability that you actually do have this cancer? How do we figure that out? Well, we're going to need Bayes' rule for this. Let's plug those variables into Bayes' rule. We've got the probability of a positive test given cancer times the probability of cancer over the probability of a positive test. And we know some of these numbers. We know the probability of a positive given cancer. It is right here. And we know the probability of having the cancer, 0.1. Whoops, 0.01. But we don't know the probability of a positive test. But we can calculate that. There's two ways to get to a positive test. So you can either have cancer and then get a positive test, or you can not have cancer and get a positive test. We'll calculate those the same way we did on the previous slides. 0.01 times 0.9 plus 0.99 times 0.2. Right, those are the two paths through the tree. Okay, so the numerator is 0.009 and the denominator is 0.207. And then we actually do the division, we get 0.043. Okay, what do you think about that? So you run the test, and it turns out there's about a 4% chance you've actually got the cancer. Let's say that was you. You go into the hospital not feeling too good. Doctor runs a test, comes out positive. You run the numbers, and of course the doctors also run these numbers. And it turns out there's only a 4% chance you've actually got this cancer. What do you think about that? It's pretty bad. 1 in 25 chance you've got it. Well, you might be thinking, let's run another test, right? Let's just be sure about this. we'll calculate that a little bit later. What's the probability that you don't have the cancer given that positive test? Yeah. Right? So you either have the cancer or you don't. So if the probability that you had it was 0.043, then the probability you don't have it is just 1 minus that. Okay, let's say you come to the hospital. Doctor says, I think you might have the cancer. Let's run this test. And the test comes out negative. What's the probability you don't have the cancer? You run the test comes out negative. What's the probability you don't have that cancer? Well, we're going to need Bayes' rule for this again. So you plug those variables into the formula. And then we know some of these numbers. Like we know the probability of a negative test given not cancer is right over here, 0.8. The probability of not having the cancer is 0.99. And then the probability of a negative test. So again, there are two paths through the tree, but we can shortcut this a little bit. We already know what the probability of a positive test is. It's 0.207. So the probability of a negative test must be 1 minus that. And we get 0.792 on the top and 0.793 on the bottom. So overall, this comes out to 0.999. Well, again, what do you think about that? Run the test, comes out negative. The probability that you don't have the cancer is 99.9%. Well, that seems pretty good. Doctor says, well, it's probably something else. Or maybe you should just go home. Okay, so that's how you apply Bayes' rule. We'll do a lot more Bayes' rule examples coming up on Wednesday. So let's do this problem. Let's say we've got a standard 52 card deck of cards. We shuffle them, and then we lay them all out in a line on the table. What's the probability that the Queen of Hearts has a red card to its right? Okay, so you take a deck of cards, you shuffle it up good, you lay all the cards out in a line, you find the Queen of Hearts. What's the probability that that card has a red card to its right? Yeah, how'd you figure that? Okay. And remember, the Queen of Hearts doesn't have to be like almost at the end. It could be anywhere. All right, let's use Bayes' rule to figure this one out. So we want to calculate this conditional probability. Now, what we're basically calculating is, first of all, the Queen of Hearts cannot be on the very end. If it's on the very end, then there's no cards to its right. So given that the Queen of Hearts is not the last card, so that's kind of like a precondition. The Queen of Hearts cannot be the last card. What's the probability of finding a red after the Queen of Hearts? So we could write out the decision tree for this. That queen is either the last card or it's not the last card. And there is a 1 out of 52 chance that it's the last card and a 51 out of 52 chance that it's not the last card. And then the next probability is, what's the probability that there's a red card after it? Okay, so if the Queen of Hearts is the last card, what's the probability there's a red card after it? 0. And therefore, what's the probability that there's a red card not after it? Right, 1, right, 1. Right, because these two have to add up to 1. All right, now on the bottom side, if the Queen of Hearts is not the last, what's the probability that there's a red card after it? Uh, 51. Why 51? Because we already used up 1 card for the Queen. And then not after is 26 out of 51. Again, these have to add up to 1. Okay, so we're looking for the probability of a red after the Queen of Hearts, which are these two branches here, given that the Queen of Hearts is not last. So it's this one here. These two? Yeah, these two here. Let's see. So there's a 0% chance that there is a red card after the Queen of Hearts because there's no cards after the Queen of Hearts. So there can't be any cards after it. And then because these have to add up to 1, this must be a 1 here. Okay, so we end up with 51 over 52 times 25 over 51. And you can run that through your calculator, but these 51s here cancel out. And you get 25 over 52. Any questions so far? Okay, so I got another problem here. This one involves 3 outcomes. And so the previous cancer problem I just kind of made up those numbers. But then I went through some medical research papers and I found an actual paper presented, like I think back in the 80s, where a doctor was trying to teach other doctors about this Bayesian rule for calculating things. And so these numbers here that you see on the screen are actual real numbers from that paper. I was really so pleased to find this paper because now I've got some real numbers. And so the problem was presented as patient comes to the hospital, presents with a chronic cough and occasional breathlessness. So they do a biopsy on the lung, which indicates either lung cancer or a condition called sarcoidosis. Lung cancer, of course, is quite serious, and sarcoidosis can be treated with antibiotics. So I'm going to use N, C, and S here to indicate whether the biopsy comes out normal, and okay, nothing is wrong. Sorry, there's 3 possible outcomes. Either you have nothing going on, you have lung cancer, or you have sarcoidosis. And then plus here is to indicate that it came out positive. So this biopsy doesn't tell you whether you have cancer or sarcoidosis. It just tells you have one of them. It doesn't tell you which. So the probability of having nothing at all is 0.991. The probability of having lung cancer is 0.001, and sarcoidosis is 0.008. And then here's the probabilities for positive test, depending upon which one of those things you have. So you come in, you got a chronic cough and occasional breathlessness. They do this biopsy, and we want to know what's the probability of having the lung cancer given that positive biopsy test. So let's set up the decision tree. So you've got some kind of disease, right? Either you got nothing, or you have lung cancer, or you have sarcoidosis. And then you can either have a positive or a negative test. And then let's see which numbers we can put in there immediately. We've got 0.991 and 0.001 and 0.008. And then a positive test, given that you have nothing, is 0.002. A positive test, given that you have lung cancer, is 0.90. And a positive test, given that you have sarcoidosis, is 0.95. So we can fill in these other numbers. This negative up here must be, oh, now I need to actually get out my calculator here. .998. This one here is 0.1, and this is 0.05. Okay, Bayes' rule to calculate this. Okay, probability of a positive test given that you have lung cancer is 0.9. Probability of actually having the cancer is 0.001. And then on the bottom, we have to calculate the probability of getting a positive test. And there are 3 ways of getting that. So we got to calculate all 3 of those. 0.991 times 0.002, that's this top branch. Then the middle branch is 0.001 times 0.9. And then the bottom branch is 0.008 times 0.95. And then I don't have these numbers already figured out, so I got to use my calculator. So 0.9 times 0.1 is 0.000309, and then on the bottom 0.991, 0.002, 0.001, 0.9, 0.008, 0.95. Add those up and we get 0.010482, and then we do the actual division and we get 0. Oh, it gave it to me in scientific notation, so I got to convert this. .0859. And then one more to calculate. What's the probability you just have sarcoidosis given the positive test? Okay, so that's probability of positive given the sarcoidosis, and probability of this over probability of a positive test. We know these numbers, 0.95, 0.008, and the probability of a positive test, we already calculated that out, is 0.010482. So let's calculate that. 0.95, 0.008, and then 0.010482. Oh, this comes out to be 0.0076, and the bottom, of course we know that, and we get 0.725. Whoa, that's a, oh, whoops, I didn't write that out correctly. All right, look at that. So if you come in and they run this biopsy, you've got about a 9% chance of having cancer and a 72% chance of just having sarcoidosis. So what would the doctor then do? What would be the prescribed course of treatment? Well, probably a pretty small chance you got lung cancer, so we should probably not start you on cancer treatment. What we're probably going to do is give you some antibiotics and send you home. And say, tell us how you feel in a week. If you get better, problem solved. If you still feel lousy, it wasn't the sarcoidosis, you come back in and we'll run some further tests to find out if you actually do have this lung cancer. So that's what the power of this Bayes rule can do for things like medical diagnostics, is now we're using hard data to inform our decisions about how to treat this possible disease. We have a biopsy we can do. It comes out positive or negative. If it comes out positive, you have one of two things. And we know that it's more likely you have sarcoidosis, it's less likely you have cancer, so we're going to kind of treat for the benign thing first, and then if that doesn't work, then we can treat for the more serious thing. So, out of today's stuff, what I wanted you to get was the things about total probability, things adding up to 1. That helps you make these decision trees. If you draw out these decision trees, you'll be able to do these problems a lot better. And then also how to apply Bayes' rule. We're going to do more complicated examples next time on Wednesday. In fact, we're going to end up with showing you how Bayesian spam filters actually work. But I want you to get the concepts for now. I'll just end with this little story that a lot of the examples that you saw today, I got out of one of those MOOC, M-O-O-C, courses online offered by Udacity. This was one of the very first courses they offered about, golly, it was probably about 10 years ago now, in artificial intelligence. And a lot of the first part of the course was on discrete probability. So I harvested a lot of these examples out of that. But I'll also tell you, I personally took that course. It's free. Took it in my spare time. And during the first chapter where they were teaching about conditional probability, just like you saw here, I was like, oh, I've got this, right? You just multiply these two things together and you get the probability. And then along comes the first test, and I completely bomb it. Just horrible. Got almost every problem wrong. And in part that was because I figured, like, I don't have to take notes. I already got this stuff. I took a stats class when I was in college. I know how to do this. But I had totally forgotten about all this Bayes stuff. And so after bombing that first test, I said, okay, I better go back and I better watch these lectures, like for real, and take notes and actually work the problems out myself. So as the instructor was working out the problems on the screen, I was duplicating all the work and running the calculations myself. Sure, I could just watch the instructor and get the answers, right? But working them out myself helped me to understand how these problems worked and how to apply the formulas. So I would encourage you to do the same thing. Copy down the problem, work it out yourself on a piece of paper or use an iPad or something like that, but actually do the calculation yourself. There's no replacement for, you could just watch someone do it, but actually do it yourself. Try doing the same problem, but just change some of the numbers. Right? Just change the numbers by a little bit and then run the calculation again. Just get used to how the formulas work and how to apply them, how to draw the trees out. I think it'll help you a lot when you're doing this. Okay, so that's it for today. On Wednesday, we'll pick up where we left off. We're going to do some more complicated examples applying Bayes' rule, and then I'm going to show you how things like spam filtering does. How does it do analysis of an email message, and how does it break that down into a probability that a given message is spam or not spam? Okay? So before we take off, are there any last questions? No? We're good? Okay. Well, I will see you all on Wednesday. Let me know what you think about this YouTube stream. I'll post links to both of them so you can take your pick as to which one to watch. Alrighty. Take care, everyone. Yeah. All right. All right. Bye-bye. And YouTube, I will see you later as well. Have a good day. Bye-bye.